In this video, we'd like to do the following example. Let's consider the Verhulst equation, dp dt equals p times 1 minus p. And I'll just denote that equation by a red star. We would like to show that p of t equals the function c times e to the t over 1 plus c times e to the t, where c is some arbitrary real number, solves this differential equation. Now, notice here that p of t is what we call a one-parameter family of solutions, because that c a priori can be any real number. And we'll see later if the interval of solution, so in other words, the maximal interval on which the solution is defined, we'll see if that indeed depends on c or if it's the same for all possible real numbers. So let's consider our function, or our family of solutions, p of t equals c e to the t over 1 plus c e to the t. Now, what do we want to do to try to show that this is a solution to the differential equation? Well, first, we want to consider the left-hand side of our differential equation star. So dp dt, and how am I going to take the derivative of this function? Of course, I'm going to use your favorite, the quotient rule. So I take the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. And I do a little bit of algebra here, and notice in the top I get two terms that are c times e to the t quantity squared, so of course those cancel, and what I am left with is c times e to the t over 1 plus c times e to the t quantity squared. So that's what happens if I simplify the left-hand side of the equation, dp dt, using my given one-parameter family of possible solutions, p of t. So now, let's leave the left-hand side alone, and let's look at the right-hand side of our differential equation, which is p times 1 minus p. So I'm going to substitute in for p, which is c e to the t over 1 plus c e to the t, and I'll do the same for 1 minus p. And now I just have a little bit of algebra to do. Notice in the parentheses here, I can get a common denominator of 1 plus c e to the t, and those c e to the t's in the numerator, those are going to cancel. So what am I going to be left with? I'm going to be left with c e to the t over 1 plus c e to the t quantity squared. And that should look awfully familiar, because that was the same quantity that we got when we simplified the left-hand side. So what we see is the left-hand side equals the right-hand side, and my conclusion is that p of t solves my differential equation for any c in the real numbers. So for any value of c, p of t gives me a solution. So that's the first thing we're going to be interested in differential equations. Do I have a solution? The next thing we're going to be interested in is, where do I have a solution? So that is going to, in general, depend on my parameter. It might also depend on the differential equation itself. It can depend on a lot of things. So let's ask this question. On what interval is p a solution? And when I say this, what I mean is use the maximal solution. So the maximal interval is what I mean. Yeah. Let me erase that. Maximal interval. So what is the biggest interval on which this function is a solution? And the answer in this case is that it depends on c. So we'll consider three cases. We'll consider the case c greater than 0, c equals 0, c less than 0. The first case is when c is greater than 0. So in this case, our function p of t equals c e to the t over 1 plus c e to the t. What we wanted, in order to determine what interval this function is a solution on, we need to think about the domain of this function. So the only way that this function can do something bad is if the denominator equals 0, right? So does the denominator ever equal 0 when c is a positive number? The answer is no. So this is a well-defined function on the whole real line. So it's a solution on the interval from negative infinity to infinity, and if you graph this function, you see that it has a horizontal asymptote at y equals 1 and at y equals 0, and I'd like you to use the definition of horizontal asymptote to check that, so you might need to review what the definition of horizontal asymptote is. And in fact, you can also figure out what that y-intercept is. It's c over 1 plus c, and you should confirm that as well. So this is a perfectly well-defined solution on the whole real line. Now let's consider the case c equals 0. In this case, our function becomes p of t equals 0, and that is perfectly well defined on the whole real line as well. It's just the horizontal line y equals 0. So in the case c equals 0, we also get a well-defined solution everywhere. The third case is c less than 0, and for convenience, I'm going to say that c is equal to negative k squared for some k being a real number. So I'm doing this just to emphasize the fact, so because we know k squared is positive, I'm emphasizing the fact that c is a negative times a positive number. So you can really see that c is a negative number. So my function in this case becomes negative k squared e to the t over 1 minus k squared e to the t. And unfortunately, this can have some problems. The denominator can in fact equal 0, and it does so when 1 minus k squared e to the t equals 0. Of course, that is the same as when 1 over k squared equals e to the t. And if you solve that equation for t, of course you get t equals the natural log of 1 over k. So you should check the following. And again, you should remind yourself of the definition of these things and use the definitions to check the following 3 items. Check that p has a vertical asymptote at natural log of 1 over k squared. Check that the limit as t goes to infinity of p equals 1. So in other words, p has a horizontal asymptote at 1. Check that the limit as t goes to minus infinity of p equals 0. So in other words, p has another horizontal asymptote at 0. And if you graph this function, it looks like this. So what can we conclude about this? We can conclude that p of t is a solution either on the interval from negative infinity to the natural log of 1 over k squared, or natural log of 1 over k squared to infinity. Why? Remember the definition of a solution. A solution, not only does it have to satisfy the differential equation, but it has to be continuously differentiable where it satisfies the differential equation. And at our vertical asymptote, our function isn't even defined, much less continuous, much less differentiable. So in this case, we can either have a solution on the sort of left-hand piece of the graph or a solution on the right-hand piece of the graph, but not both.